Let us discuss ScalarDB objects and data access. In the previous session, we discussed ScalarDB objects such as storage, namespace, and table. In this session, we will discuss ScalarDB's data model and design considerations in order to maximize its advantages. This is a conceptual diagram showing a namespace and multiple tables defined within it. The table used in this explanation has P1 and P2 as partition keys, C1 and C2 as clustering keys, SI as secondary index, and V as column value. Let me explain them one by one. Let us consider partition keys. In this example, two columns are used as partition keys, but there can be a single column as partition key as well. A partition key is required in ScalarDB. Partitioning depends on the database in which the data is actually stored. Data is divided and managed based on the partition key value, so the partition key must be decided with careful consideration. If the NoSQL service distributes the contracted throughput evenly to each partition, unbalanced partitions will be a problem. The uneven traffic will reach the upper limit of the throughput allocated to the partition, causing throttling. To avoid this, you can increase the contracted throughput, but then the remaining two partitions will not be able to consume that allocated throughput, and it will be wasted. In a partitioned environment, you also need to be careful when running queries. A query that completes within a single partition is good. If a query can be executed on a single partition, it will not only run faster, but it is also likely to be cheaper in terms of database resources consumed. Hence, it is important to partition your data appropriately. However, if the required information is spread across multiple partitions, querying across partitions indicates a bad query. In some cases, you may need to query across partitions, but such queries should be the exception. If you frequently need to query data across partitions, it may be more performant and cost-effective to copy the data to another container with a different partition key and query it. Storage is cheaper than request units. Clustering key. The clustering key uniquely identifies a record within a partition. In this example, a two-column clustering key is specified, but a single column is also sufficient if a unique row can be identified using that. If a row can be identified by the partition key alone, it is not necessary to set a clustering key. Records stored within a partition are sorted by the clustering key column. In this example, we can identify one record with partition keys as P1 equals 0, P2 equals 0, and clustering keys as C1 equals 0, C2 equals 1. When we use a term as primary key, we actually refer to the combination of the partition key and the clustering key. The primary key uniquely identifies each record. A big challenge in managing databases is how to provide efficient access to stored data. ScalarDB offers secondary indexes as an alternative way to identify target records stored in the database. In this example, the secondary index value 2 is used to identify the target record. The interface available in ScalarDB cluster has Java API as its core component. The SQL API operates above that, and Spring Data JDBC for ScalarDB operates on top that. In this session, we will discuss Java API to understand the basic internal working. The Java API provides the following commands for CRUD operations. It should be noted that the read operation is explicitly divided as get and scan operations. These two operations provide different functionality. The create, update, and delete operations can be considered similar to other DB operations. ScalarDB's data model is an extended key-value model inspired by the Bigtable data model. It is similar to the relational model, but differs in several ways. This example looks at a table with two partition keys, two clustering keys, one secondary index, and a column V that stores the target value. In this example, we will learn the most primitive and fastest data access method. The most basic access method using ScalarDB is by using the primary key, which means partition key and clustering key in a specified order. First, the target partitions and records are narrowed down by the partition key. Next, the search is further narrowed down by clustering key C1. Finally, the target record is identified by the clustering key C2, and the value of column V can be accessed. The get operation must identify the target record, so if you do not specify the second clustering key C2, an exception will occur. Next is the scan operation. It operates on multiple data records using the read operation. The data is accessed using three main approaches in scan operation. The first approach is to use a combination of partition key and clustering key, which we discussed earlier in the basic get operation. The second approach is extracting the data using a secondary index. The third approach is scan all using cross-partitioning. The where condition is a search condition that can be used in addition to the basic access method. First, similar to get operation, we will discuss the basic access method using partition key and clustering key without using where condition. Specify the partition keys for the filtering condition first. You cannot define a subset of partition keys when a filtering is done based on partition keys. In this example, for records are returned based on the filtering done by using the partition keys. In scan, you can add a subset of clustering keys as a filtering condition. If the C1 column is added as a filtering condition, 2 records are returned. When the C1 is the last clustering key column for the filtering condition, it is possible to use range conditions as well. Now, the C2 column is also added to the filtering condition. It returns 1 record. The result is the same as get operation. If C2 is the last clustering key column in the filtering condition, it is possible to use range conditions as well. We will discuss more about the where clause now. There are differences how where clause is handled by RDB and NoSQL databases. In an RDB, queries containing where clause are properly pushed down to the target database. All filtering conditions, including the where clause, are executed in the RDB, returning only the required results. On the other hand, with NoSQL database, filtering is performed at the ScalarDB layer based on the results of conventional partition key or clustering key, index, and scan all operations. The results are returned to the application. Therefore, if the amount of data retrieved from NoSQL database is large, attention must be paid to performance and costs. As mentioned earlier, RDBs and NoSQL databases handle filtering differently. When dealing with such cases, we not only need to consider the amount of data, but also need to consider whether to use an RDB or a NoSQL database. The following table shows the supported data types in ScalarDB and their mapping to the data types in case of other databases. However, the following data types in JDBC databases are converted differently when they are used as a primary key or a secondary index. This is due to the limitations of relational databases.